Good afternoon, and that's East Coast time. I realize we've got some folks out in Central and Western time zones. My name's John Cotter. I'm with the Vermont Public Utility Commission. Today is the first in a series of 5 webinar presentations in Vermont Public Utility Commission case number 21-3883-Rule, which the Commission opened to develop a rule for energy storage facilities as directed by the Vermont Legislature in Act 54 of the 2021 legislative session. The Commission is hosting this 5-part webinar series in conjunction with the U.S. Department of Energy Office of Electricity Energy Storage Program and Sandia National Laboratories. Over the course of this webinar series, we will be hosting presentations on topics covering the current and expected state of energy storage technologies, the installation and operation of those technologies, interconnection and aggregation of storage and how that affects the grid, and national and regional best practices. We are conducting this webinar series remotely using the Teams platform. We will be recording these presentations and making them available to the public as soon as we can post them. We will provide information on how to access the recordings as soon as possible. If you do experience technical difficulties today, I encourage you to try and reconnect to the platform. Given the large number of attendees, we will not be able to halt the presentations for any one person that is experiencing difficulty with their connection. In the event someone is unable to reconnect, they will have access to the recordings of each session once they are posted. Please keep your cameras and microphones turned off during the presentation. This will help save bandwidth and as well as real estate on the screen, depending, of course, on your settings. My name is John Cotter. I'm a staff attorney and Deputy General Counsel at the Vermont Public Utility Commission. I am joined today by Mary Jo Kralewski, Utilities Analyst, and Dominic Gotti, Department of Energy Clean Energy Innovator Fellow. Also joining us today and doing the heavy lifting, not just today, but throughout this webinar series, are several representatives from Sandia National Laboratories. I'd like to thank them in advance, not just on behalf of myself, Mary Jo, and Dominic, but on behalf of the entire Commission for the extensive work that they have done to prepare this series, as well as the work they will do throughout the course of the next several weeks. We would not be here today without their efforts and expertise. Broadly speaking, today's presentations will focus on an introduction to storage technologies, including siting issues and some discussion of use cases, and then a presentation on policy trends and the regional implementation of FERC Orders 2222 and 841 and their implications for distribution utilities within ISO New England. Your presenters for those topics will be Mr. Eric Sporkey and Mr. Will McNamara. We will have approximately 10 minutes for questions and answers at the end of each of their presentations. We will also have a brief introductory presentation by Dr. Emery Juk, who I will introduce to you in a moment. Because we have such a large number of folks in attendance today, we will be prioritizing questions from those who have been actively participating in the Commission's rulemaking process so far in case number 21-3883. If you do have a question, please enter it into the chat function and make sure to type your name and your affiliation before you begin typing your question. Please understand we are time limited and we have a lot of material to go through, so this is not an opportunity to express opinions or offer comments. Rather, it is an opportunity to ask clarifying questions in response to the materials you hear today. We will be establishing a schedule for moving the rulemaking process forward after we conclude this webinar series, and there will be opportunities at that time for providing comments and recommendations on what the rule should include. Of course, you are always welcome to file public comments into the case at any time. With that said, I would like to take a moment to introduce Dr. Juk. Dr. Juk is Chief Scientist, Energy Storage at the United States Department of Energy Office of Electricity. Dr. Juk has spent his professional life passionately tackling important problems as a researcher, teacher, and program manager. He is recognized as an international leader in the energy storage field and has decades of experience leading the energy storage program for the Department of Energy. For the past 2 decades, he has directed the Electrical Energy Storage Research Program in the Office of Electricity, developing a wide portfolio of storage technologies for a broad spectrum of applications. Dr. Zhuk has devoted over 3 decades to the innovation and advancement of energy storage technologies, connecting diverse small businesses with federal objectives and resources, with a remarkable record of success supporting development and transition of technologies from the early research and development stages to commercial success in the marketplace. With that, I will hand things over to Dr. Zhuk. Doctor?
Hello, thank you for this excellent introduction. It's always a pleasure to be contacting with Vermont. Can I ask whether this is my presentation? Do I have the screen, or do I have to say next?
You'll have to let me know when to change.
Okay, I was going to share.
Oh, go for it then.
Okay, take it off and I will share. You have to allow me to share.
Should have access to do so. I'm sorry.
Does this work?
I'm not seeing anything from your end.
Okay, forget it then. Bring my presentation up again.
Yes, sir. Oh, can you see your screen?
Yep.
Awesome.
Okay, here we go. We are talking about the future, and we are talking about the future of the electric grid and its energy storage. Next, please. Next. Dylan, are you having problems?
No, it's transitioning. Are you not able to see it?
Oh,
You're on
sorry.
You're on the voltaic pile from Volta.
Okay,
Yeah.
got it. Okay. Batteries go back to about 1800. Next, please. And as you can see, all of the important types are already there quite a while ago. This is the lead acid battery. Next, please. This is the Leclanché cell, or zinc manganese oxide. It's already there in 1866. Next, please. But during the early 19th century, the DC grid was essentially born. And this allowed electricity transmission over large distances. And batteries, on the other hand, were relegated to use in cars. Next, please. Okay, the grid used to be a simple structure, and it was deterministic. You had fossil fuel generation, you had load, and in the middle you had transmission. And that basically was it. Next. During the early 20th century, renewable generation was born. Plus or minus a few years. Some of us were doing photovoltaics even earlier, but that's about right. Next, please. And suddenly the grid became much more complex. On the one hand, it's not just fossil fuel generation, it's also renewable generation, wind, solar, geothermal, what have you. And on the load side, it's also more complicated because we are introducing distributed generation, rooftop solar, and electrification in general via electric vehicles and what have you. And it's not enough anymore to just have transmission between those. We need storage. Next, please. And why? It's because energy storage provides energy when it is needed, just as transmission provides energy where it is needed. Next, please. So we have been burning coal, oil, natural gas for our electric grid, for transportation, for buildings, for industry, and basically for everything. And that's the Industrial Revolution. But it has a very unpleasant side effect. If you look at the carbon dioxide in the air, which we've been putting there, its level is now twice of any of the highest level in the last 800,000 years. Next, please. And as a result, we must decarbonize. We must change to renewable energy. We cannot afford to have any more carbon dioxide in the air and the climate change that goes along with it. And we have to do it soon. Next, please. Along with electric generation, all other sectors must also decarbonize. Buildings, transportation, agriculture, manufacturing, everything is going to be reliable on renewable electricity. Next, please. But of course, we know that renewable energy is variable, particularly on the diurnal scale. We are not going to be able to rely on solar during the night. And so energy storage becomes a necessity. Next, please. Energy storage has finally gained international acceptance. It's taken us 20 to 30 years. Next, please. And here it is. Gigafactories in the US. The North American battery initiatives. And they're all over the place and they're large. Next, please. And it's the same thing in Europe, Australia, China, Korea. Next, please. And here it is, the European gigafactories map. 20 gigafactories that are being proposed. That's quite a lot of batteries. Next, please. A cumulative deployment of storage is continually increasing around the world. Next, please. And it's going to be something like this with all the countries participating. Next, please. But the question is there. Is there a limit to how much lithium we will need and how much we can produce? And with that, the floor is open for Eric Sparky to go further into depth. Thank you.
Great. I love seeing those historical perspectives. They're a little terrifying sometimes, but they certainly motivate where we came from and where we need to be. What I'm going to talk about today is really trying to give you folks an overview of lots of different storage technologies, some of which you will have heard of, some of which maybe will be new to you, and sort of present a little bit of just here's what's on the table and what our options are as we're continuing to move forward. And can you guys see my screen?
Yeah.
Yes, we can. Mhm.
Great. All right. So one of the things I want to emphasize is, although I'm going to talk about just a ton of different technologies today, it's going to be really pretty quick overview. This is such a fast-moving field that honestly, by, in 2 months, if I were to give this talk, it'll be different. It'll be updated. There will be different technologies coming and going. There will be more or less of different activities. So that makes it really exciting, but it also makes it something that you really kind of have to keep your thumb on the pulse of things to really understand how the situation is evolving and where the opportunity space is. Lots of these companies that I'm going to talk about and technologies are in still relatively early stages of development and demonstration. But like I said, within a couple of months, some of those will have been deployed in different situations. And really every month there's updates to what companies are putting together. So this technology set, it highlights a little bit of different technologies. I've put a couple of pictures on this title slide of some installations in Vermont already, right? So this new EVLO system that's going in, this is one of the first lithium iron phosphate systems that I'm aware of that's been put in for grid scale, and as contrasted with the picture on the right there that you see, which I believe is a more conventional lithium ion battery. But certainly batteries is one of the areas that we'll talk about today, not just lithium ion, but some of the other candidates that you may not be as familiar with. All right, so when we talk about energy storage for grid scale applications, there's really about 4 different classes that we often break this down into. So one of those is gravity-based, sort of mechanical storage. There's chemical, typically hydrogen-based storage, thermal energy storage, and then what I call electrochemical or battery-based storage. So we'll kick things off here a little bit, looking at these gravity or mechanical-based systems. And that's really, quote, the king on the hill, if you will, is pumped hydro storage. This is, until recently, it accounted for more than 90% of the storage in the United States. The rapid growth of battery-based deployments in the last couple of years has put a pretty big dent in that. It now represents a little over 2/3 of the electrical energy storage in the country. But the concept is you basically pump water up a hill, hold it in a lake, for example, and then when you want that potential energy back from the water that's up the hill, is you let the water run back down, and it turns a turbine and allows you to reclaim your energy storage. So the virtue of this is you can do this on very large scale. So the systems that are in place are very old, but they are capable of enormous amounts of stored energy. So for example, the big system in Bath County, Virginia is capable of 24 gigawatt hours of stored energy, which is a lot. That's enough to supply quite a lot of energy to quite a lot of places within that region. I'm excited to say that, well, I should say one of the challenges to this is that you have to have a big hill, typically more than 1,000 or 1,500 feet of elevation drop, and you have to be able to put in a lake. You can't always do that everywhere. You can see in the map that I have on the right there a number of different locations where pumped hydro storage is put in place, and some people are really challenged with trying to find new places to install this on this very large scale. There are, however, some alternatives that still use this concept of pumped storage in different alternatives. So this company QuidNet has actually been trying to make a more modular system where instead of pumping water up a hill, is they pump it down underground into what amounts to cracks in the water. So can you see my cursor?
No. No, unfortunately.
I'll take that as a no, and we'll change that out here. How about now?
Yes.
Great. All right, so you can see they pump the water down into this crack in the substructure of the earth. Often it's an old oil or natural gas repository, and they line this essentially with some rubber coating, basically, and they pump the water down there, and the weight of all of this earth, basically, as they flex that up, it provides the potential energy they need, so that they're using basically the weight of all of those layers of earth to provide their potential energy. So they pump it down to store it, they release it to bring it back up, and so they can make systems that are on the order of 1 to 10 megawatts with 10-hour plus modules. Now, all of these systems I'm going to talk to you today, if you look at the websites and a lot of the demonstrations, they all advertise the same basic application set, right? There's no question the biggest application opportunity right now is with renewables integration, probably followed by backup storage. But part of those includes things like, power quality and frequency regulation, sort of serving as a buffer to help moderate supply, demand, transmission, congestion, those sorts of things. It's playing those roles in grid storage. But sort of the general topics that I would argue that are being prioritized for these large-scale systems, where we need ideally more than about 2 hours of storage, maybe more than 4 hours of storage, is about grid resilience and renewables integration with backup power included. So this is one example of an alternative to pump storage hydro. There's another idea that I'm pretty excited about, and this is that instead of pumping water underground, essentially what you do is you rely on the pressure of water to create your potential energy. So essentially you can imagine you have a couple of tanks that are down below, and it doesn't have to be in the ocean. It could be in a lake. I know Vermont doesn't have a whole lot of ocean, but it does have lakes. So if you were to go down, say 100 meters, there's a significant amount of pressure accumulation there. And so you pump water out of the containers, and that creates the potential energy because the weight of the water above wants to shove that water back in. And then when you want to release the energy, you allow the water to rush back in. And those potential energy changes are used to drive turbines. There's a company called RCAM. There's a couple of companies that are working on this, but RCAM is one of these that is looking to install these sorts of systems off the coast up in the Northeast near New York, particularly where it could be integrated with offshore wind. So this is another alternative that I think is pretty exciting. You don't just have to lift and release water. You can also lift and release heavy rocks, for example. So this company Ares, and I recognize that this is one of those companies that somebody has put forth and said this is not recognized as a suitable technology for Vermont. So that was put forth by the, seems to have slipped off of my, Efficiency Vermont R&D report. Recognized that there were a couple of things. This one in particular, they seem to be concerned about what happens when it gets cold and icy. I'm confident that the folks at Ares would have a different opinion about that. But I do want to mention that you can basically take these railroad cars, fill them with dirt, haul them up a hill, and it's the same principle as the pump storage hydro, that you then release that potential energy being up the hill by letting these railroad cars run down the hill again. And instead of running it off of a turbine the same way, they're running it off of motors that are driven by the rails and cables associated with the Ares system. Different ways that some of you have seen for lifting heavy dirt. This one got a lot of publicity. Energy Vault. This is another one that report deemed to be unfeasible based on how big and tall these apparatus were. This particular sort of spidery looking configuration where they were stacking blocks on top of each other has sort of gone by the wayside. They have transitioned now to making a great big building. This sort of looks like, imagine elevator cars that are raising and lowering heavy loads and then storing them on the different floors of the building. This is not fantasy anymore. They are actually building a very large system in China. So this is going to be a 25 megawatt, 100 megawatt hour system in Rudong, China. And so you can see on the pictures on the right, they haven't finished the assembly yet or the construction, but that's going to be a very large system that they're installing there. And I'm excited to see how that advances. That type of energy-based storage. In terms of sort of overall mechanical storage, we all know about compressed air energy storage. Once again, this is a technology that was recognized as maybe not being suitable for Vermont, particularly for underground compressed air storage, where the idea is that you take air and you pack it down and you basically compress the bejesus out of it. The potential energy of that compressed gas then can be released to reclaim the energy that you want. And turn turbines and reclaim that energy. So underground storage, of course, it requires that you have to have a large, a mine or a reservoir, a cavern that you can store energy at high pressure underground, and that's not geographically suitable for all locations. There are a couple of large examples that have been around really for quite a long time, since 1978 to 1991, as you see on the top. The location in Germany is a shorter discharge time, but is a very large, high power system. And the system in McIntosh, Alabama, is intended for very long duration discharge time. So quite a lot of energy storage that can be managed there. There have been lots of different proposed systems for compressed air energy storage that you see here. So you see in that red box, a lot of these have not been realized or have been discontinued. There are some that are certainly active, and they're growing significantly in Asia. You'll notice there are two very large systems that are being proposed. So that green circle highlights gigawatt-hour systems, multiple gigawatt-hour systems in Texas and in China, that those are intended to basically provide quite a lot of non-battery based compressed air energy storage. And I do think that that's going to be a technology that moves forward and really gives opportunity because it can be a really large scale system. It also ties into other types of storing gases, right? So this concept about where we're going to store gases relates also to hydrogen-based storage. Now, hydrogen is a little bit tricky, in my opinion, because it's not just storage, and it gets a little bit confounded in that regard, because for hydrogen storage, you have to first generate the hydrogen, for example, by electrolyzing water. Then you have to store the hydrogen that you've generated, and then to reclaim the energy, it's not as simple as just turning a turbine, as you actually have to perform chemistry again. With a fuel cell, you can use a turbine, or typically the turbine is powered by the burning of the hydrogen. And so you have 3 different steps where you can lose efficiency on this. And that's really one of the big challenges that people are going after here, is how do they improve each of those different steps to increase the overall efficiency. So electrolysis right now is about 70 to 80% efficiency, and they're working on improving that. And the last step of re-electrifying the hydrogen is about 50% efficiency, possibly as high as 60%. The second one, the one in the middle, that bulk storage, is also a challenge because we got to make sure that the hydrogen isn't leaking. Hydrogen leaking into the atmosphere is not good for upper atmospheric global warming gas generation. And so it does need, each of those steps needs to really be carefully considered and improved as we're thinking about hydrogen storage. But it does have tremendous potential, no pun intended there, if we can make this work effectively. So this is an example of a project called IPP Renewed that's being sort of a collaboration between folks in Utah and in Southern California. And the concept is that they're going to use renewable, say, wind and solar in Utah to generate lots of hydrogen and pump it down into these subsurface salt caverns, which can store an enormous amount of gas. These are very large, very stable caverns that can hold up to 500 million kilograms of hydrogen. That's a lot of hydrogen, okay? And so they're originally going to start putting in natural gas, and eventually then they will transition by about 2045 to putting in just hydrogen. But conceptually, they want to bring those up, and the energy that they store there, they want to transmit down, as you see in that little line in the plot on the right, all the way to Southern California. So understand that if you combine storage with transmission, you open up the doors to lots of different opportunities. I know that's a concept which is very familiar to folks, especially in northern Vermont, is the idea of generating and transmitting storage where it's possible. But the idea here would be that this could allow for really multi-day or seasonal storage, and this addresses a very real challenge in Southern California that's exhibited by this graph, where you can see they suffer from significant seasonal and multi-day weather events that really impact what's going on with their renewable generation opportunities. So having access to the large amounts of energy that you could store with, say, hydrogen in this case, or even things like compressed air, pumped storage hydro, these really big systems that can store multiple megawatt hours of energy for very large systems is attractive. Another system which is potentially capable of really big systems is thermal storage. So thermal storage has all kinds of different flavors. We could give a whole talk just about any one of these, and thermal storage certainly qualifies. One of the more conventional ones that people talk about a lot is storing heat in molten salts, particularly nitrate salts, where these are what get used with concentrated solar power. So essentially you use concentrated sunlight. Imagine using mirrors, the old Archimedes argument that he could roast ships in the ocean by shining mirrors. Well, they do that for real. They don't roast the ships, but they do use that to generate enormous temperatures in excess of several thousand degrees that are concentrated, and they can use that to heat salts. They store the heat in these high heat capacity salts, and then when you want them, you can use those. You run them through a heat exchanger that there's a variety of different types. You can use supercritical CO2. You can use steam generation. There's lots of different engines and generators essentially that you can apply to these hot salts, and it'll allow you to pull electricity back out of that heat. There's a number of examples that are shown here. Spots in Arizona, Morocco, Nevada, these locations that have large systems that are being put in there. So more than a gigawatt hour in many cases of these storage. And I don't believe I have a slide on this right now, but a year or two ago, I know that there was evidence that something like 22 installations for these sorts of things are going into China. So this is a rapidly growing, aggressive concept of how we would use concentrated solar coupled with thermal storage to drive a combination of generation and distribution. But again, this is not necessarily ideal for every location. This is an example of the site in New Mexico where we do a lot of this testing. And the reason I bring this up is a different type of medium that you could heat instead of salts, which are sometimes a little bit hard to store. They can be corrosive, which just makes them, again, hard to store. And so there are some challenges about that. And there's also some limits to how hot you can make those salts before you start running into volatility issues. They are chemical agents in that regard. And if you heat up a liquid hot enough, in most cases, you're eventually going to get some significant vapor pressure. You can resolve that by heating particles. And so one of the things that Sandia is working on is the idea of, instead of running salts through that tower, is you could actually run particles, these sort of ceramic fancy dirt, really, that they can run through there. And this sort of graphic on the right is showing that as sunlight shines through an open window onto a floating bed or a floating sheet of these powders and these particles, then they can take those particles, store them in the hopper, and again, reclaim that heat through heat exchangers, or even use those as media for industrial processes, so industrial heating. You don't just have to do that potentially in small particles, but there are folks that are looking at using great big rocks, basically big pieces of dirt, if you will, to store large amounts of energy. I really get a kick out of this. This is from Siemens Gamesa, their ETES concept. I love that they call this the new Stone Age, because they're heating stones. They basically generate very hot air that they blow through the rocks that are inside and underneath that concrete bunker that you see there. And those hot rocks then will hold energy for quite a long time. So they can store for discharge of up to 24 hours with nominal power of greater than 30 megawatts, quite a lot of capacity in there. And in Hamburg, Germany, they've got an example of where they've got 1,000 tons of rock at 750 degrees, reclaiming that heat with a steam turbine, and it allows them to generate up to 24 hours of storage at 1.5 megawatts. So that's not bad. To sort of get that kind of storage out of there. And these are systems that are gaining some attraction around the world. You don't have to store those rocks above ground. There's a system that Sandia has been developing for some time called therms, where the idea now is to store the energy underground. Sandia is certainly not the only agency that's looking at this, but you effectively pump hot air down into these, what we call thermoclines, and these allow you to store heat in different regions of the terrestrial landscape. And then you can pull that out again by blowing new air through that, reclaiming the heat that's in the rocks, and then you pump that up, and you can either use it for process heating, building heating, or regeneration of electricity through steam. So those are very large-scale systems. There's a couple of other things that I think are actually pretty exciting as far as thermal storage. This is a creative approach from a company called Antora that is heating graphite bricks. So graphite is produced on enormous scales. It is very environmentally friendly in that regard, and it holds an enormous amount of heat. So these are commonly used already. There's no supply chain issues with these. And what they're doing is heating these up to over 1,000 degrees to the point where those black bricks turn red hot. They glow. Anybody who's ever looked inside of a really hot furnace knows just how intense the light can be coming off of that. And what they're using here then is to take that heat and either push it out and use it for industrial process heating, or they're using it, actually they're using the light. So they open a window and then they put these thermal photovoltaic panels basically in front of that window, and they collect the light coming off of those very hot bricks. And it's a very efficient way. They've set world records now for how much energy storage or how much efficiency they can get out of those panels. It's over 40% efficient for reclaiming electricity from that light. And they're considering this. They've got a couple of really pretty interesting demonstrations. There's a big installation that they're putting in, I believe it's in Texas, on a farm where they can use these systems either for electricity generation or for process heating for a lot of the different processes they need to use for managing their crops. So when they have to heat up and dry out or whatever it is, anneal basically a lot of their farm products, they can use the heat from this system to try to drive some of those processes. So a neat example, this one, they're moving pretty aggressively towards that. There are other companies that are also looking at this. So Electrified Thermal Solutions, ETS, is a company that basically just heats up different bricks, sort of more like conventional ceramic bricks instead of carbon. And they're also using that for industrial process heating. This is a company out of Sweden that they're not heating bricks. They're actually heating a molten alloy. And so they can make these modules out of this system that are capable of about 13 kilowatts of power that'll run for 13 hours. So conceptually, they want to tie this together with a lot of renewable integration. They're demonstrating that in Sweden, Morocco, and in Asia at UAE. And so they're using this essentially with a little bit alternative approaches. So using a Stirling engine as the way to recollect the heat from their molten alloys. And because they're using a specific, what we call a phase change material, as the way to store this, is they don't have to heat it to quite such high temperatures as you do, for example, with molten salts, but you can store the energy because of the nature of the alloy and the material. Is the phase change that it undergoes really allows them to collect and store quite a lot of energy in a relatively compact unit. So you see some graphical images there shown. Those are not terribly big, and they're well integrated, for example, underneath solar panels. And this is a system that Azelio is really pretty excited about. You don't just have to use hot storage to store energy. There are other ways to go about this where you can use cold air. So this is from Highview Power. This is a concept where essentially you take air and you actually pull heat out of the system, and you can store and collect that heat, but you can also then use the refrigerated air that you've got in there. It gets compressed, and so you can hold on to that. When you want to recollect the energy, essentially you recombine the hot and the cold, and you allow that to drive a turbine that recollects your energy. So conceptually, I want to make the point that you can do cold storage. Maybe that's a little more appropriate, perhaps, in a place that can be chilly like Vermont, and as well as hot storage. And companies like Highview in particular they have been advertising this for some time. They're still eager to try to get some of these pilots installed. This is getting into some of the same challenges as compressed air. At the end of the day, the liquid air really is a very highly compressed form of compressed air. All right, so other technologies we want to consider. That's a lot to digest already, but the big hitter that a lot of people have paid a lot of attention to. There's a lot of noise around batteries. When we think about batteries, they're not conventionally thought of very much for really large-scale, long-duration applications, but they certainly have applicability around kind of that mid-range storage. So certainly we're seeing demonstrations with lithium-ion on the 2 to 4 to possibly as many as 6 or 8 hours of storage. That will likely grow in coming years. But there's lots of different technologies we can pursue. And on the left, I've listed a number of those that I'm going to try to highlight at least relatively quickly here to give you some perspective on what's on the table and where they're finding some traction in terms of emerging industry. So if we look at basically how much storage we have, boy, is this an impressive chart. So if you look at how much storage we started with just 5 or 6 years ago, really not that long ago, it was inconsequential. And already by 2022 and into 2023, there's an enormous amount. We are basically at a rate where we're almost doubling the amount of deployed storage that we're going to have in the United States. Now, that's really exciting, and these are big numbers. So at the end of Q2, for example, in 2023, we had 11 gigawatts or 31 gigawatt hours of installed storage. Now, you'll notice if you do that math, you'll notice that's less than 3-hour duration for most of what we're installing, which means it's probably mostly lithium ion, right? So that 2 to 4 hour range is really the sweet spot for a lot of those technologies, and that's what's growing most aggressively. Okay, now we still have about 22 gigawatts of pumped storage hydro as potential replacement for those gigawatts of generation. But if you now take that 11 gigawatts versus the 22, you can see why I said we're only at about 2/3 of the energy storage capacity in the United States is represented anymore by the pumped hydro. Okay, so this is where we are, and this is great. There's still a lot more storage that's planned. This is a plot that came out of a recent NREL report that I have referenced down there, and it highlights as a function of different types and distributions of renewable energy integration and what those goals might be as a function of which decade we're in, 2030, 2040, 2050, how much of each type of storage might we need? And you can see this actually predicts that by 2050, we're expecting to need 6 terawatt hours of storage. That's 85 times more than we have today in order to hit renewable targets of 94% clean energy renewables. That's a pretty aggressive target, but doesn't seem wholly intractable if you think about it. So if we now look at how many batteries, can we make enough batteries to basically get through this? These are values from McKinsey & Company that just came out, I believe, this year. And we're in 2022, we have about 63 gigawatts of manufacturing capacity in the US. And by 2030, there's an expectation that that number should grow so that the total amount between China, the US, the rest of the world, we could hit about 6.5 terawatt hours of manufacturing capacity. Now, the tricky part of that is that about 4.5 of that is probably going to go to electric vehicles. Okay, so there's a big challenge in there saying, yes, we can make a lot of batteries, but we're going to use a lot of that for cars. So if we want to think about battery-based storage, which is really great because it's agile, it's adaptable, it can be high power, we're going to have to think about some other technologies. Now, lithium-ion is certainly coming on, really gangbusters, right? So the idea of large-scale systems is no longer a fantasy. These are going in, these are being demonstrated and installed and used at large scale around the world. These are some examples of, multiple megawatt systems that have been installed, really pretty big systems that are going in addition to sort of the supply chain issues and the manufacturing limitations we might have to pay attention to for these really big systems. We are still cognizant of the fact that, these challenges are still coming up. These things are having some issues with fire-based failure. They're learning to sort of moderate this. I do notice so there was one of these Tesla Megapacks did catch fire earlier this year. This particular picture is not from this year, it's from 2021, but it's a similar concept. And I will say one of the things I'm excited about is you'll notice of all of those packs, only one of them is on fire. So they're learning how to engineer this a little bit to minimize what is recognized as an inherent vulnerability of some of these systems. And so those sorts of engineering solutions, I think, are going to be important as we try to reach out towards other technologies. If we think about other systems, though, that are candidates, lead acid has been on the table for a long time. This is, as Dr. Zhuk pointed out, this has been around for a very long time, over 150 years. They're not very energy dense. They don't typically cycle very much, but it's still an enormous market. It's over $40 billion a year in the lead acid market. We all know that it's useful for cars. It's still in many of our, under the hood of many of our cars. And it has off-grid uses for things like traffic signals and railroad communication, backup power. But it is finding some grid integration applications as well, and for renewables, for load smoothing, time shifting. And it's really just based on a highly recyclable, very robust chemistry. We know this stuff pretty well. And even as it will increase in efficiency and in cycle life through some R&D that's going on right now and in being invested in. It's a technology that isn't applicable all around the world, but it is something we don't want to dismiss. So lead acid batteries, I think, are not going away. I think they're just going to evolve. There's another one that you hear about a lot, which is sodium-ion batteries. It's often seen as sort of a drop-in replacement for a lot of the lithium-ion batteries. It has significant potential advantages. So as sodium-ion batteries are slated to come out today, they're probably not as high power as lithium-ion batteries. They might be a reasonable replacement for some of the lower power systems like lithium iron phosphate, which maybe makes them more appropriate for things like grid-scale storage. They are expected to have improved safety. They're expected to have a little bit lower energy density, but they should be lower cost for a number of reasons that apply in terms of how you assemble the batteries, what kind of current collectors you use, and of course, the global availability of the ingredients that we put into a sodium-ion battery are expected to be less, let's just say, socioeconomically complicated, and so there's good availability of sodium. I think it's fascinating to realize that the United States has something like 93% of the world's entire supply of sodium carbonate, which is one of the ingredients you might use if by parallel to lithium-ion batteries to make a lot of the cathodes, the anodes, the electrolytes that we put into these materials. So there's an opportunity for the United States to really invest in these sodium-ion systems. There are a lot of people who are investing in these systems, and this is a plot that came out from Wood Mackenzie late last year or early this year, and it's basically showing up to a projection of 40 to 100 gigawatt hours of manufacturing capacity of sodium-ion batteries, largely coming out of Asia. So most of these companies are from China, with a few exceptions in Europe and one in the United States. So there is opportunity about how to move this forward. Part of what's challenging about this is that not very many of these have actually been deployed or manufactured or tested. So although there's a lot of excitement around this, finding actual data that really describes how well they work in grid scale systems, what their safety is, This is still an active area where a lot of people are going to be looking at this more closely, especially in about the next 2 to 3 years. I'm very interested to see how these batteries really stack up, no pun intended, and perform versus the lithium-ion systems. The US company I mentioned is a company called Natron. They make a little bit different kind of sodium-ion battery. And one of the things I like about these is, although they're not meant for very large-scale, long-duration systems, they are extremely high power. So I would never use this to try to make a 100 gigawatt hour or a gigawatt hour storage system, but they can generate a huge amount of power. So when you couple this with other things, these have really interesting applications, almost like a supercapacitor that I'll mention here in a second, where you could couple this with a higher energy density system and offset, for example, diesel startup and shutdown processes. So you could offset a lot of CO2 production using these high power systems to sort of address, you're starting up a crane, or you're dealing with something in the oil and gas industry, or you've got a black start situation and you need high power quickly. These really allow you to couple that with a higher energy density system. And I think this is an exciting technology. I did mention supercapacitors. I'm not going to spend a lot of time talking about this because a lot of their applications are pretty similar to what I just described. So critical infrastructure for very shorter duration, high power applications. And certainly they typically would be coupled with a higher energy density configuration. Molten sodium batteries is another sodium system. It's been around for a long time. And these are exemplified, for example, by what NGK Insulators, who's now partnered with BASF, a German company. So Japan and Germany have teamed up in this case, basically to try to get more deployments of these higher temperature molten sodium systems. Now, the beauty of this is they've already got over 700 megawatts and almost 5 gigawatt hours of deployed storage in over 200 sites around the world. They just put in a monster big system in Abu Dhabi, which is over 100 megawatts and almost 2/3 of a gigawatt hour in the Middle East there. So that's a pretty exciting system. They're moving forward very aggressively with that, and their costs have come down significantly. So that's a system that has very high rate and very large scale. So they typically are around 6 hours of discharge time. These are really big systems that they can install and run, and they've been running these they actually have installed data integrating especially with wind in Japan for over 10 years. I think it's probably closer to over 12 years by now. So this is one of the few systems, along with a flow battery out of Sumitomo, that really has decades of data that show how well these systems work. They are well proven. Sodium nickel chloride is the other sort of long-standing molten sodium battery. You may have heard of it as a Zebra battery. And there's a company out of Europe that's actually been manufacturing this. There's now actually a whole consortium of companies that are trying to develop alternatives to these molten sodium batteries. They're looking at an alternative to the Zebra chemistry. And so this consortium of, I believe it's 15 different companies in 12, or there it is, it's 12 companies or partners rather in 7 countries in Europe are working on making these sodium zinc systems. And so this is another version of these molten sodium chemistries that I think is going to make a really big difference. Okay, zinc-based batteries. If you imagine taking a AA or your D battery, imagine if you could take that, something so cheap that we buy them, at Walgreens by the dozens every year, and we throw them in the garbage because they're safe or we can recycle them. That makes this a really attractive class of chemistries. And it turns out the zinc chemistry field is extremely diverse. So there's zinc manganese oxide, which is essentially a variant of what goes on in those little D batteries. So uses cheap, high energy density materials, and companies like Urban Electric Power out of New York have been working to try to develop these systems. They've got doing a lot of work in backup power, but you can see up here, renewables integration, backup power, grid stability, and behind the meter applications are really where each of these different zinc-based systems is trying to make impact. If you want to get away from zinc manganese oxide, zinc nickel, although nickel is a little bit more difficult to get your hand around, just with sort of the global supply chain volatility. But companies like Zinc 5 or ZAF, AZR, they're sort of partnered together, or companies like NZinc are really trying to push for these zinc nickel chemistries, which again are probably focused more on things like backup power and behind the meter applications. Zinc Air has the potential to be very large scale, longer duration systems. So companies like Zinc8 and eZinc, even ZAF, are looking at sort of that 24-hour application space. So very long duration, larger scale systems. And we'll talk about that again in just a moment. Zinc bromine has sort of two configurations. There's a sealed zinc bromine, which is kind of a self-contained battery, if you will. And companies like EOS are putting together fairly large systems out of zinc bromide. So they're aiming for 10-hour storage, really meant for things like solar integration or wind integration. And they've got some demonstrations going in, for example, in California. Redflow is a company out of Australia that's using similar chemistry, but they've put it into a flow battery configuration, and we'll highlight that a little bit later. But same concept of using fairly inexpensive materials. These are both successful companies that are putting together real demonstrations. Zinc ion is still fairly emergent. So Salient and Enerpoly are both European companies. I believe they're European. I might double check that. One of them might be out of Canada. But in any case, these are still sort of coming on board. They have not really made the same impact, but if they did, they could be, again, sort of a grid scale replacement for some lithium ion because of the cheap abundance and high energy density of 2 electrons in zinc as opposed to 1 electron in lithium. If we get to sort of metal air batteries, I mentioned a little bit about the zinc air, but another chemistry you've probably heard about is these iron air systems that Form Energy is trying to produce. And the concept here is that they're using air and rust essentially as the ingredients of their battery, trying to reversibly oxidize iron. I can tell you, having tried to do that myself, if they've managed to do that, that's really pretty impressive. It's not a small challenge. And they are building, the picture on the right you see is the manufacturing facility they are building in, and I kid you not, the Rust Belt in West Virginia. So they're putting this system together and really trying to make iron air a system that targets explicitly at least 100 hours of storage. So when we're talking about really long duration, multi-day outage, those sorts of things, this is a concept that Form Air is really trying to push. Flow batteries is another one that I mentioned already briefly, but conceptually here you have lots of storage in external tanks, and you bring the contents of those tanks, which is a liquid, has dissolved electrochemical species in it, you bring those together to a central reactor, and based on how that reactor is put together, you can change how much power you get out of the system. And there's lots of different chemistries you can pursue here. There's vanadium redox flow, which you've probably heard about. Also things like zinc bromine that I just mentioned, iron chromium, iron flow, transition metal chelates, some other different chemistries. There's over 100 different companies that are trying to put out flow batteries that have the advantage of separating the capacity of storage in those tanks from the power in your storage that's determined by that reactor I mentioned. And so really being able to decouple those things makes this a very flexible and potentially attractive scalable system that could resolve a lot of different systems. You see here an installation from Redflow with their zinc bromine chemistry, and here is a very large system going in again in China that is intended to up to, well, right now it's at about 100 megawatts and 400 megawatt hours of storage that's intended to power up to 200,000 residents a day in China. So really a lot of storage capacity in there with these vanadium redox flow systems. And the last one I'm going to touch on here, I know I'm going long a little bit, is these molten metal batteries. These are less common than you may have heard about. This is a company in Massachusetts called Ambry, and they're using basically molten metals at higher temperature. So they're using actually molten calcium and then a calcium antimony alloy, and their separator in this case is actually a calcium chloride salt. Those details may not be important to you, but what really is valuable about this is that this is a scalable system. It has reasonably high power, as you can see in the metrics that are there on the right. It operates across a very wide external temperature range. So these don't require the same sort of heat management that you like with HVAC and so on you might need for lithium ion. And it allows this very broad temperature range for application. Any of these higher temperature batteries, so the molten sodium batteries I mentioned that typically run around 300 degrees, or these batteries that run at higher temperature like this up around 500 degrees, you can run those in British Columbia or in Abu Dhabi. It doesn't really matter. The battery itself is designed to maintain its own temperature, and they're much more forgiving of some of these external environmental factors. But these are also designed to be very long life, so they're designed truly for 20 years of sealed life. It's got awfully fast response times, and I really like the opportunities that this kind of chemistry is presenting as a really robust inorganic system. There's nothing in this that can really degrade over that 20 years. So to be honest, they're advertising 20 years. I bet you in 20 years we'll see a lot of these installed systems. For example, Microsoft has a data center that's putting these in. Xcel Energy in Colorado is putting a system in. as these are going together, I expect in 20 years we'll still see these things running strong. Okay, so that's an awful lot of information covering gravity, mechanical storage, chemical and hydrogen storage, some thermal energy storage, and then a lot of variety in electrochemical and batteries. And with that, I'm going to go ahead and stop. And if we want to have questions now, or if you want to wait till the end, I'd be happy to entertain that. I do want to sort of highlight anybody who's interested in learning more about the sodium and zinc batteries. There's going to be a workshop that NatBat is putting together later this month already down in Houston. So we would love to see any of you who are interested there. All right. Thanks very much.
Great. Thank you so much, Eric. Yeah, let's take a few minutes. We got a few questions in the chat for you. Again, I want to answer these or present these based on the highest order of relevance to the PUC rulemaking. So the last couple of questions that came in, Anthony Roisman is from the Vermont Public Utility Commission. First, he's got a two-parter. He asks, has the iron air battery in Minnesota gone operational?
No.
Perfect. Next question. What about the waste disposal issues for these different systems?
Wow, that's a really important question. Everybody talks about, yeah, how much does it cost to install? How you dispose of these things matters. So paying attention, people are starting to recognize that when they're done, they got to figure out what to do with this. So just for example, with sodium sulfur versus sodium nickel chloride, we make the argument that sodium sulfur is made out of all this dirt cheap material. That's true, which means there's nothing in there that's of value to recycle. The nickel chloride chemistries, for example, even though the nickel is more difficult to get a hold of, people want the nickel, so there's actually a financial incentive to recycle those. So paying attention a little bit to this whole trade-off between dirt cheap as an incentive versus recyclability is another issue. Almost all of these chemistries that I talked about, though, either there is now a recycling plan. If you go to each of their websites, they'll talk about components that are recyclable, or they'll talk about basically the environmental safety, that they're non-hazardous components, the zinc manganese oxide that you could effectively throw in the garbage when you were done. You probably wouldn't, because we'll try to reclaim the zinc. But those are concepts that everybody's paying attention to. There aren't a whole lot of these that I would really be very worried about in terms of end of life as a hazardous material that you have to dispose of. Some of the ones that have molten alkali metals in them, we got to pay a little bit of attention to how those are handled, but just for safety concerns. But those are well-known industrial processes for handling things like sodium or calcium or some of those materials.
Awesome. Great. Thank you so much. I got another one in the chat from Vikram Linga, who is from DOE, who asks, what is the RTE estimate for the pumped hydro alternatives?
They typically vary. Most people will advertise. If they're advertising, they typically advertise somewhere between about 80 and 85% for cell level RTE. In fairness, for the batteries in particular, trying to get a handle on whether they're talking about cell level performance or system level performance, sometimes that's a little bit obfuscated with the data that they present on their websites or they make publicly available. Each of the other systems, the hydrogen alternative, the round trip efficiency, if you go all the way from generation to back, through storage and back to electricity, that round trip efficiency is pretty low. It's going to be closer to on the order of about 30%, assuming you don't have any leakage. So that one is an area where they're really working to improve that. The thermal energy storage, those depending on the effectiveness of your heat exchanger. I've seen numbers for those that are anywhere between 70 and 90% round trip efficiency. And again, it depends a little bit on how they're choosing to extract the energy, but the potential is there for those to be very high efficiency systems, particularly if they're well engineered. Does that get enough of an answer for you? I can follow up with you on any particular technology that you're interested in.
Great, thank you so much. Let's see, moving forward, Charlie's got a couple of questions, one for you and one for Dr. Zhuk. I'll start with the one for you. Charlie Vartanian, formerly from PNNL, asks, what discharge hour range do you consider long duration? And what do you consider an ideal discharge duration in hours to address current renewables integration challenges?
Boy, those are two loaded questions. My personal opinion is that sort of short duration now is 2 to 4. Medium duration is probably, I would say, 4 or 6 to about 12 hours. And then long duration storage is going to be on the order of more than 10 hours, more than 12 hours. And then there's really a longer duration than that, which is the seasonal storage, and that's going to be multi-day. So I talked about a few examples of those that cover much of that spectrum. But for me, what I consider just sort of standard long duration is probably longer than 10 or 12 hours. And the second part of that question was what?
Yeah, the second part of that question was, what do you consider an ideal discharge duration in hours to address current renewables integration challenges?
So current renewables, right now, the market really doesn't support very much today, longer than about 4 hours. But part of that is because the percentage of renewables is not yet as high as it needs to be. There's still an awful lot of fossil fuel opportunities or nuclear opportunities that are providing high enough baseload that that 4 hour duration is kind of letting things be successful. I would say though, and in fact, Paul Denholm at NREL just gave an interesting talk last week at our peer review meeting, and he highlighted that there is going to be an opportunity for some of these longer duration systems as the market evolves a little bit. And so I'm expecting that on that order of 8 to 12 hours is probably going to be important for the renewables integration. Never mind longer term outages and these so-called Dunkelflaute events where it's both not windy and dark.
Great, thank you so much. Eric, I got one more question for you in the chat, and then Charlie, we'll circle back to your question for Dr. Zhuk to close out this Q&A right now. But Todd Olinsky Paul from CISA asks, it's a little bit of a big one, so bear with me. Are the duration limits of lithium-ion batteries due primarily to market factors like monetizable applications are of short duration, technical factors, the technology doesn't scale well for longer duration applications, or economic factors, it becomes uneconomic to build longer duration lithium-ion batteries? If lithium were cheaper and more plentiful, would long duration be a problem?
For lithium-ion batteries, they really are. There are some limits for a conventional cell. For an individual cell, there are limits to how much you can basically pack in there. So the duration of discharge, there's a technical limitation for today's version of a lithium-ion battery. As we get into other systems that might use, lithium metal anodes, and the energy density can go up a little bit, some of those things shift a bit, but you can engineer around that, right? So I can take a bunch of shorter duration, say 4 hour discharge systems, whatever it's going to be, and you can engineer those into a system that allows you to get longer duration storage. And that's where the other parts of your question come into play, at least in my opinion, and that is that some of that other engineering is not economically rewarding because a lot of the policies, the regulations, and the market opportunities are really only supporting engineering to enable about 4 to maybe 6 hours of storage today. It's growing. It used to only be 2 to 4, and now that's creeping up to 4 to 6. So that's evolving a little bit, and the market case for that, I think, is going to reflect some motivation to try to engineer lithium-ion batteries to allow longer duration storage. But fundamentally, if I had my druthers and all things were equal and we were inventing these all from step one, I probably wouldn't pick lithium-ion for long duration. I'd probably pick them for the very high power, sort of shorter duration applications that they are really just absolutely world changing for. The other thing I do want to mention is that if we're going to get into these long duration systems, we have to ask the question is, does it make sense to use the batteries that we need for cars? Does it make sense to use those to power something for 12 hours of renewable integration if we could instead use something like a flow battery or a sodium battery or a zinc battery, or a pump storage hydro system? I think that there's better ways to use the resources that we have available where we really need them. And I like to say to stop putting the lithium square peg in the grid storage round hole if we have other round pegs to put in the correct hole. We just need to get those other pegs pieced together yet.
All right, great. Thank you so much, Eric. And looks like that's all the questions I have for you. So again, big round of applause. Thank you so much for your presentation and your time today. Really do appreciate it. Dr. Zhuk, are you still on the phone? I do have a follow-up question for you.
Yep,
if we have
I'm
time.
here.
Perfect. Our friend Charlie Vartanian, formerly PNNL, also asks a question to you. He says, does the OEES program scope and support include electromechanical and thermal in addition to electrochemical energy storage technologies?
In principle, yes. Electrochemical, of course, we are looking at virtually all of the technologies that Eric mentioned. Thermal storage, we track them. and we may play with them. Mechanical, we have done compressed air in the past. In fact, we did the first experiments in compressed air, other than the two famous batteries, the two famous installments that everybody has, one in Germany, one in Texas. But so yes, we do all of the above, but some of the larger ones become hard to afford, and therefore we only do bench shop models or coin cells or what have you.
Great. Thank you so much for that. Appreciate it. Looks like we're out of questions for now. So thanks everybody for sticking in there with me. And we're going to transfer over to my colleague, Will McNamara. Will, the floor is yours.
Yes, thank you, Dylan. And hello, everyone. It's great to be with you today. I first want to say thank you to the Vermont PUC for hosting us today for this very important series. Thank you to Eric for providing that excellent overview about energy storage technologies. I'm now going to transition into a conversation around energy storage policy and sharing some thoughts with you about state and federal considerations. Dylan, I presume that my presentation is up?
Yep, I can see it. I can see you, and I can hear you just fine.
Terrific. Okay, so what I'm going to be covering today is a general discussion around state level energy storage policy considerations, giving you kind of a current status of what's happening at the state level. I'm going to talk about federal and wholesale issues, primarily through ISO New England's implementation of FERC orders 841 and 2222 and their direct implications a deeper dive that we're going to have on December 7th, in which we will really be going into detail into the New England policy issues. We're going to assemble representatives from other New England states to share their perspectives on how they're developing regulations for siting, interconnection, operation, and aggregation of storage, some of the best practices around policymaking and the coordination between states and the wholesale market. So a lot more to come. This is really an introduction into some of these important policy topics. Just real quickly, I'd like to introduce the Policy and Outreach Group at Sandia to you. We provide educational outreach services to state regulatory commissions, such as the Vermont PUC. We've been doing this now for several years and have engaged a number of states on their efforts to develop these frameworks. We do a considerable amount of policy analysis and thought leadership. We are supporting states in their decarbonization modeling. We integrate with other federal policy groups. We work very closely with the other national labs. And of course, we support the Department of Energy through the Energy Storage Grand Challenge and other efforts. I'd like to acknowledge that all of this work is sponsored by Dr. Emery Zook through the U.S. Department of Energy Office of Electricity Energy Storage Program. So we thank him very much for his support. So as I talk frequently about energy storage policy, I always like to start out by saying that the U.S. electricity market is not homogeneous. It's very risky to make broad generalizations about what's happening because there are very distinct differences between states. We have regulated states and we have restructured states, and they are approaching the topic of energy storage along with other topics very
very differently. So in regulated markets, we have what we call vertically integrated utilities that maintain the ownership and control around generation, transmission, and distribution assets. They are heavily regulated by states, public utility commissions. They're very much motivated by cost recovery that is obtained through rate base, through their surcharges to customers. And the PUCs in those states really can very significantly direct utility action and investments. Now, we compare that to the restructured markets where oftentimes utilities are prohibited from owning those generation and transmission assets in order to enable competition to take place. The RTOs, regional transmission organizations, and independent system operators in those regions play a very significant role. They are responsible for the interstate transmission facilities and heavy oversight from FERC, the Federal Energy Regulatory Commission. And within those restructured states, the role of PUCs can tend to vary a bit. So with that setup, I'd like to just reiterate the fact that the states are approaching the topic of energy storage differently. In regulated states, I would offer that the emphasis is typically placed on distribution system, reliability issues, and resilience. And energy storage is approached from a vantage point of it needs to solve a problem, again, mostly around the distribution system. Now, in restructured states, there's a greater emphasis that's placed on revenue creation, making money, finding a way for the financial viability of these storage assets. So that kind of, again, reiterates that we have to be very clear about what state we're talking about with the regional implications as well. Let me see here. Now, the analysis that we do at Sandia looks at the evolution of state policymaking specific to energy storage. I would offer that there is a trajectory here when we look at all 50 states. On the far left end, we have states that either have done nothing with regard to energy storage policymaking, or they've just started to demonstrate an interest in the topic. That evolves to the right-hand side of the trajectory that becomes, very sophisticated policymaking, states that have integrated energy storage into a number of their policy programs, et cetera. I would offer that the vast majority of states are still in this left-hand side of the trajectory. As we start talking about long-duration energy storage, that becomes even more the case. Very few states have done much with regard to long-duration energy storage policymaking. And even with short duration, I would say that there's really a less than a handful of states that have reached that highest level. I would argue that it's California, New York, Hawaii, that really can be singled out as having reached that top level. So just for a current status report, where we stand in terms of state policy making, there are 19 states plus the District of Columbia that have adopted a decarbonization goal. A decarbonization goal can either be 100% renewables or 100% clean energy, with the latter allowing for nuclear energy to have a role. Now, interestingly, among these 19 states, not all of them have set policy for energy storage. So it's kind of a case where they've made a great headline or public announcement that they're going to work toward achieving decarbonization. But yet when you peel the curtain or peel the onion behind that, there may not be a strong energy storage policy framework to support that effort. Now, there are 15 states that have adopted what I would define as a substantive energy storage policy framework. And in all of those cases of the 15, they exist within a state that also has a renewables policy, typically a renewable portfolio standard. Now, in the 15 states where we are seeing energy storage policy activity, they are tending to focus on three core policy levers, if you will. There are utility procurement mandates, targets, or goals. In other words, that's when a state will say that they are going to pursue X amount of energy storage through a mandate, a target, or a goal. And we have 11 states that provide examples of that. The three of those 11 that are in New England are Connecticut, Massachusetts, and Maine. The second lever that I would point to is financial incentives or subsidies. These are state level incentives that are being offered by the state out of a state fund to stimulate the development of energy storage projects. And we have 4 examples of that in California, Maryland, New Jersey, and New York. Thirdly, I would say that state-funded demonstration projects are really the third level energy storage policy lever that we have witnessed. And those are evidenced in Massachusetts, Maryland, New York, Utah, and Washington State. So there's 5 examples of that. I would say another policy that deserves mention is requiring energy storage to be included in utility integrated resource plans. That's becoming a bit more common, and we have 2 states that I'm aware of, Nevada and New Mexico, that have made that requirement. You'll see, though, that I think a real strong case can be made for where we are seeing the development of energy storage projects is correlated to those states that have developed strong enabling policy frameworks. So where is the development happening? Using those figures that Eric pointed to and Dr. Zook as well, it's primarily concentrated in the California region and the PJM region. And I would argue that it's primarily due to the fact that states in that region of PJM and California have very welcoming policy frameworks that are bringing in the developers. Now, Texas, we could spend a whole conversation around Texas. Texas is a unique market. It is also right up there in terms of deployment. But Texas is an exception in the sense that it's not been driven by policy factors as much as business conditions that are really well suited for development of energy storage. There's not a capacity market in Texas. It's heavily focused on the energy market with arbitrage transactions. Also, the ability to take an existing legacy fossil fuel plant and transition that into a renewable plant is really happening in Texas, and that's also driving storage. But 8 gigawatts of utility scale battery storage was expected as of 2022, and a further 20.8 gigawatts by 2025, again, really concentrated in California, ERCOT, the New York ISO market, and of course, ISO New England. Now, I mentioned those 19 states that have adopted decarbonization goals. They are listed here for you. I've highlighted the ones that are in New England. And interestingly, as you'll see in the far right column, as I said, not all of these states have strong energy storage policy frameworks. I would say that in Connecticut, there's somewhat of a program emerging with some financial subsidies. Maine, very little from what I have witnessed. Massachusetts is definitely up there with a somewhat developed plan. It has the procurement mandate that I mentioned, and Rhode Island, very little to if anything. So that underscores the fact that while a state may have a decarbonization goal, there's still a lot of work that's left to be done in developing energy storage policy frameworks. Now, of course, we're here talking about Vermont. Vermont is also a very unique state, as you well know. It's the only state in New England that has chosen not to restructure its electric industry by adopting retail competition. And so in that case, Vermont utilities own few of their own generation resources. They participate heavily in the New England electric wholesale market, and therefore they do share many characteristics with distribution companies in other New England states that have restructured, even though Vermont is technically not a restructured state. Now, Vermont is served by over 20 utilities. Green Mountain Power is the largest. It's the only IOU, and it serves about 3/4 of the state. Vermont gets nearly all of its electricity from renewable energy, with 3/4 of it coming from firm renewables. But interestingly, more than half of Vermont's electricity is imported, with most of that coming from Canadian hydroelectric power facilities. Now, legislation was passed in 2020 requiring Vermont to reduce emissions down to these levels that I'm showing here on the right, with 80% below 1990 levels achieved by 2050. So clearly the case for energy storage in New England as a whole is well established. Energy storage will definitely be needed to balance out the increasing levels of variable renewable generation expected in the region. The numbers that I found based on the ISO New England reports were that in Vermont specifically, 125 megawatts of energy storage was proposed or earmarked to be achieved as recently as 2021. If anything, that number has increased. It's certainly not gone down. So as we look at energy storage policy making opportunities, gaps, and barriers at the state level, here are some high-level messages that I'd like to emphasize for you. Certainly, the momentum has begun. It's continuing. We see state legislatures and regulatory utility commissions showing this increased interest in promoting energy storage to bolster decarbonization efforts and promote market stimulation. We typically or oftentimes see high-level goals either adopted by the legislature or a governor, and then they're handed down to the regulatory commissions to implement those goals. And I would say that, while FERC and what's happening at the wholesale market is very, very important, and I'm going to talk about that shortly, the activity at the state level is really key here as well, because when we talk about putting steel in the ground, the actual projects that are going to be developed, it's oftentimes much more directly impacted by what's happening at the state level than what's happening at the federal level. Unfortunately, we continue to see that there are disconnects between state policy and federal policy that really need to get ironed out. And in the absence of ironing those issues out, it creates some market confusion and perpetuates some barriers that have existed. And what I mean by that is, there's oftentimes a lack of uniformity across states, even within a specific region. And this can create a kind of a patchwork of a marketplace that is not conducive to energy storage development and may actually make developers more averse to going into that region. So it's incredibly important to have interstate coordination within any one region. Now, in the work that I do for Sandia, I have identified 13 policy levers that, to one extent or another, are being utilized by states to promote energy storage. I'm not going to read through these or go into great detail about the 13, but it relates to a survey that we conducted earlier in 2023 as a partnership with CESA, which is the Clean Energy States Alliance. They are right there in Vermont, and my colleague Todd Alinsky-Paul, I believe, is still on this meeting. We conducted this survey earlier this year with a focus on decarbonizing states. We really wanted to highlight, what are the best practices, what are the barriers, and get input directly from these states that ultimately would underscore the urgent need to expand energy storage policymaking to support decarbonization. And so we conducted this survey and we published this report. It is publicly available to you. Respondents came from state utility commissions, state energy offices, and government offices, governor's offices, along with some industry respondents as well. And the survey resulted in a number of very interesting findings that I would like to just summarize here for you. The survey responses came from a wide range of states. Back to that trajectory that I shared with you, some of these states have very little, if any, energy storage policymaking. Others are quite sophisticated. We included both in front of the meter and behind the meter storage in these survey questions. And so the perspectives that we received were very diverse and really showed a wide range of objectives, how energy storage is being used, and terrific insights into the maturity of some of these policies that are existing. You can see the states here that were participants in that survey, and it really underscored a lot of the findings that we had suspected to be the case, that some policy levers really seem to be prioritized more than others. Again, I would say that it's the procurement mandates, targets or goals, incentives and tax credits, and those, kind of state-sanctioned programs, whether they be demonstration programs or other analysis programs looking at cost-benefit analysis for energy storage. Number 2 and number 5 on this list are interesting to me because they're somewhat double-edged swords. We found that when a state has a very definitive policy around utility ownership of energy storage, that can almost be a detriment to the market development because third-party developers see that as a negative. That is the response that we receive. Furthermore, when a state prescribes specifically where energy storage development should take place, that can also, tend to have a negative impact on market development because it may not always flow where the market opportunities are. The state may be looking at it from a reliability or resilience perspective, whereas the market developers are looking at it to create revenue. But I would also want to share some of these high-level observations. Again, I'll say very strongly that there's a general acceptance that energy storage, particularly long duration, is going to be a necessary tool to achieve decarbonization. That's only gaining more and more momentum. even those states that have pretty robust policy frameworks, they told us that they're still seeing significant challenges in bringing energy storage to scale within very aggressive decarbonization timeframes. Most states that we heard from told us that they're still grappling with how to deploy sufficient amounts of energy storage, including both in front of the meter and behind the meter, to achieve their decarbonization goals. Interestingly, when we talked with states that have not done much in terms of policy making, there were some common reasons why that is the case. First of all, there seems to be still a lack of clarity around which use cases or applications for energy storage are best suited within specific regions to serve decarbonization goals. There remains a perceived high cost of energy storage, even though the data shows that prices for batteries are on the decline. There's still this perception that it's too expensive to pursue energy storage. There's also a feeling that we heard that, well, energy storage is something for the future, but not today. And finally, we heard that they're still kind of taking a wait and see approach in terms of evaluating what are the best practices for energy storage, looking at what other states are doing. And, I would just reiterate the fact, back to my previous slide, there are 15 states that have substantive policy frameworks for energy storage, leaving 35 states that do not. And so there's still quite a bit of policy inertia that is happening, not as much aggressive activity as I think is going to be necessary. So just to kind of round out the survey results, in terms of the industry feedback that we heard, clearly there was pretty unanimous agreement that developers are going to those states that have welcoming storage policies. In fact, supportive state policy is really essential to building energy storage markets. That's a theme that we heard time and time again. The industry respondents also said to us that they view states with decarbonization goals or policies as generally more welcoming than states without. Furthermore, incentives or tax credits being offered at the state level were singled out as being the single most helpful type of energy storage policy lever. So that's very interesting feedback that we heard. The industry feedback told us that utility ownership, the stringent ownership restricting it to utilities, is perceived as the least helpful policy that's in place because developers would argue that that is perceived as unfair competition. Also, wholesale market policies are very important. We heard Texas as an example of a state that, even though it lacks storage policies, it's very attractive due to the wholesale opportunities that are afforded in that state. So that is a very important study. It's the first of its kind, as far as I'm aware. Again, I invite you to obtain it online. I'll leave you, as I transition now into federal topics, just some high-level considerations from a state perspective. State utility policymakers are continuing to consider how energy storage can support broader clean energy goals within a state. Taking the time to consider whether or not the current regulatory structure allows for energy storage to compete on a level playing field based on legacy policies in that state. And furthermore, really ensuring that the state agencies are engaging stakeholders, the right stakeholders, anyone with an interest in energy storage to come to the process, have a voice that's represented so that the ultimate policies reflect that. And then actions that those considerations result in would be developing a roadmap that identifies policy, technology, and process changes, determining what specific policies that need to be adopted in that state, and again, taking those steps to ensure collaboration with all stakeholders. So I am now going to transition into a discussion around federal topics. Vermont is, of course, also impacted by what's happening federally, primarily through the FERC orders and rules that are being set by the New England ISO. So just to recap, ISO New England handles wholesale electricity while retail activities fall under the Vermont PUC's jurisdiction. The ISO New England does not own or operate energy infrastructure, and it does not decide where projects should be developed or how they should be, where they should be sited. Rather, the ISO New England looks at the system, does studies of the transmission capacity, making sure that power can reliably be moved across the region, and also developing those tariffs, the market rules that will facilitate the involvement of energy storage and provide a value for various transactions. So what is happening at the federal level that's directly relevant to this conversation is that there are two FERC orders that have emerged that are particularly significant. The first is FERC Order 841, which was released in 2018. It directed RTOs to remove existing barriers that would prevent energy storage from participating in wholesale markets. So it directed those RTOs to look at their rules and tariffs, and anything that was preventing energy storage from participating, they had to revise those rules. So the RTOs were asked to establish rules that open capacity, energy, and ancillary services markets specifically to energy storage. Now, this rule did not apply to those vertically integrated states that are not part of an RTO, and Texas is a state that did not fall under this FERC jurisdiction. Secondly, the order that's really important to be aware of is FERC Order 2222, and that was released in the year 2020. Now, this order is focused on aggregated distributed energy resources, which typically fall in the range of 1 kilowatt to 10,000 kilowatts. This order is intended to create a pathway for energy resources that can be aggregated across multiple smaller facilities to become a single market resource. In other words, a DERS aggregate. The DERS aggregate can then offer a portion of its output into the wholesale market. When combined into an aggregation, the output and activity of these multiple DERs can satisfy minimum size requirements and other performance requirements that may have been previously established by the RTO. So these are both very significant orders that have been in place, which are radically changing the way that wholesale transactions are taking place and allowing for energy storage to participate. So there are direct implications with energy markets, ancillary services, and capacity markets across the RTOs, and in particular, the ISO New England. You can see the kinds of services on this chart that typically are associated with those three market types. Now, where we stand today is with regard to Order 841, FERC has accepted ISO New England's compliance filing, and it is set to start January 1st, 2024. I don't want to minimize the process that it took to get to this point. It's several years in play, but they're finally at a point now with ISO New England where they do have acceptance of the filing. And so starting in 2024, storage assets will be eligible to participate in one of two primary models within ISO New England. There's what is called the binary storage facility model, and this is for technologies that cannot operate continuously. They are therefore comprised of both a generating asset and what is called a dispatchable asset-related demand facility, typically a pumped storage hydroelectric facility. The second option is what is called the continuous storage facility. This is for technologies that are capable of charging or discharging at any megawatt level. Typically, this is where we're seeing the lithium-ion battery storage deployments being eligible to participate. Now, interestingly, the last report that I saw, no entities have registered to participate in the binary storage facility model for ISO New England. 31 new entrants have registered to participate as continuous storage facilities. ISO New England also has developed what's called a storage as transmission asset only, or SATOA filing. This would allow for batteries and pumped hydro to participate, but they really would be allowed to only serve a transmission reliability purpose, and then would therefore be restricted from participating in those other markets, the energy capacity and ancillary services market. However, in the available time that I have, I really think it's important to focus more heavily on Order 2222 rather than 841, because in my opinion, the implications for both utilities and state regulatory commissions is far greater through Order 2222 rather than 841. And it's because of the role that both utilities and state regulatory commissions are going to need to play in order to effectively implement this order. So when we talk about these distributed energy resources and how they would be aggregated, we're talking about on-site generation, battery storage, demand response, electric vehicles, and energy efficiency. They could all work together to be aggregated to participate in those wholesale markets. FERC's definition of a distributed energy resource is any resource located on the distribution system or any subsystem thereof, or behind a customer's meter. And the data indicates that within ISO New England, DERs are largely split between energy efficiency and solar generation, with energy efficiency being the slightly larger resource. So on this chart, I know there's a lot here, and this presentation will be made available for you to look at in greater detail. But a couple things I just wanted to emphasize for you. Microgrids are absolutely considered a form of DERs. They fall into the on-site generation category. Other interesting things that the order says is that an aggregation can contain a single resource if it meets those minimum size requirements, and it allows for heterogeneous aggregations, meaning, you know, the different types of DERs can combine together. So I think that that's really important to note. But there's no question that Order 2222 raises a number of jurisdictional issues between federal and state regulators. So again, to be clear on the line between the two, under the federal side with FERC and the RTOs, they are responsible for developing the rates for wholesale transaction sales. They are also in charge of determining that the necessary metering and telemetry plans that are proposed by the RTOs are sufficient to accommodate aggregated DERs. Now, on the state side, so this would fall under the Vermont PUC's domain, there is responsibility for reliability and safety of distributed energy resources, any potential cost impacts on distribution systems, the state interconnection rules that obviously create a pathway for these resources to get connected to the grid. Now, states cannot regulate which DERs can participate in wholesale markets or how they can do so. That falls back to the federal entities to regulate. But you can see where the points of interconnection are, there's multiple points where state policy is going to be impacted by federal policy and vice versa. Again, this is kind of an eye chart, but it's something that I want to leave you with and highlight, what are some of the parameters and requirements coming out of Order 2222 that still need to be addressed. There are bidding parameters accounting for the physical and operational characteristics of DERs aggregations. There's a host of information and data requirements that still need to be satisfied, those metering upgrades that I mentioned. And then really, from a broad perspective, coordination between the ISOs, the DERS aggregators, distribution utilities, and the state and local regulators. So not surprisingly, Order 2222 is still unfolding. There is not final or full approval as of yet for ISO New England's compliance. It is still pending at FERC. FERC gave preliminary approval to ISO New England's filing, but highlighted a number of areas that still require work. They are related to the minimum size requirements. So, what would be the limits set on those aggregations? FERC has said that they should be as small as 100 kilowatts. And so in order to accommodate that, there is still some policy work that needs to be done within the ISO New England. Locational requirements, so areas within which those DERs can be aggregated. And again, the metering and telemetry requirements coming out of the utilities still all need to be addressed. So it's probably still a year or two out. The implementation timeline for ISO New England is set for 2026. And they continue to work on the revisions to their filing that FERC has requested, specifically changes being made to the energy and ancillary services markets. Again, those minimum requirements, utility opt-in requirements, and information around data requirements. What kind of data coming out of the aggregated DERs is going to be necessary. Also, there's this concern around double counting, where any particular resource or aggregated resources would have opportunity to both be compensated through the wholesale market and potentially compensated through retail rates. And so there's a need to figure that out, which is risen up to the level around the conversation of sub-metering requirements. In other words, having not only the behind the meter meter, but also a sub-meter to track those transactions and prevent the double counting. This is proving to be very complicated. FERC has established that these behind-the-meter distributed energy resources are resources with a point of interconnection located behind the retail delivery point. And so, in other words, it requires a sub-meter. However, the utilities have been saying that it's really not feasible within the time frame that they're shooting for, that 2026 time frame, because this is a whole system upgrade that needs to take place. There are other protests around this that are saying sub-metering is not a viable option because DERs would be dependent on this host utility to set up this system, and that prevents the DERs from getting developed. So kind of how this has all resulted is that FERC has basically said to ISO New England, go take a look at what PJM has done, what NISO has done, and the California ISO has done. They have figured it out. You need to figure it out as well. So that is very much a pending issue within ISO New England. I already talked here about the double counting issue, which remains as well. Taking this up to the level of importance and relevance to this conversation within the Vermont PUC, there are a number of impacts and implications that Order 2222 is creating. On the utility side, utility planning has to change dramatically so that instead of this centralized top-down resource planning that has been in existence for some time, utilities really need to now start looking at the complexity created by multiple DERs being on their system. And let's keep in mind that we're talking now about the potential to add hundreds of gigawatts of scale over the coming decade, the potential to add thousands of small resources that all have to be monitored and controlled. In practical terms, this means utilities are going to need to know where the DERs are located on the grid, their size, how they're being operated, and do all of this in real time. So there's a tremendous need for clear line of sight into both grid hosting capacities, customer demand, as well as end-use energy needs behind it, all of which is unprecedented. These are new challenges being placed upon utilities. Really, the step one need, to put it most simply, is that utilities have to develop a baseline understanding of their grid by collecting data via nodal modeling and existing smart meters. Some are more advanced in this than others, but they have to establish this baseline understanding in order to accommodate Order 2222. And as I said, really capture each resource, register them internally, register their mapping for aggregates, and then ultimately pair that up with wholesale market rules. So that's just touching upon the immediate impacts on utilities. There are other unforeseen implications that I'm certain are still going to be identified. Now, looking from the PUC's perspective.
Hey, Will, just want to give you a quick time check here. We only got a few minutes left. Are we close to the end?
Very close to the end. I will wrap it up. And sorry for running a bit long. So state impacts are a number of them. The PUCs are going to have to work with the ISOs and RTOs to develop compatible requirements. There's going to be new policies for DERs, including data access, interconnection rules. Utilities undoubtedly are going to need enhanced programs, whether it be meter data management systems, GIS systems, and so then they would be coming to the state commissions for funding requests. There's a real need for standardization across a region and increased increased need for distribution system analysis. As I said, hosting capacity studies, defining priority zones, and again, many other unforeseen implications. Number of policy issues that are raised here. How much control should utilities have over how DERs are serving the wholesale market? How often and at what scale DERs should be dispatched to serve the bulk power grid? What are the hard boundaries that should be established between payments for wholesale transactions and retail transactions? When there are jurisdictional questions, who ultimately gets to decide? There's an ongoing question around, is this an overreach of FERC's authority? So you see, these are very complicated issues and a very aggressive time frame to resolve them in. I'll leave you with the fact that the energy storage policy landscape continues to evolve. Sandia tracks all of these issues, and we have a database that you can go to for updated policy information. I will stop there and see if there's any questions for me.
Great, thank you so much. Yeah, I got a couple of questions. Hopefully we can get through these relatively quickly.
Okay.
Thank you so much, Will, for that
Sure.
awesome presentation. Let's see, looking in the order that I have prepared, let's see. Let's start with Riley Allen from the Vermont PUC, who asks, given the diversity of emerging storage technologies and the emerging and dynamic character of storage needs, should policy be setting simple targets or incentives, or working to identify markets or planning frameworks that foster the attributes of storage that are most needed? Should more storage be the goal, or should the most valued storage attributes be the goal?
Well, I would argue, and this is my personal opinion from what I've seen talking with multiple states, I would argue that it's the latter. I think that there's been enough evidence now to support the case that procurement mandates alone are not effective in and of themselves. We're really now at the point where we have to get a better handle on where resources should be cited, how they should be used. So, whether or not just kind of a blanket target is put into place, more importantly is understanding the use case applications for these resources and getting them cited in the most important zones. There are a number of states that have looked at procurement mandates and ultimately decided it's not necessary for them or not appropriate for them. And I can't argue against that.
Great, thank you so much. Got another question here from Doug Smith, Green Mountain Power, who asks, Slide 7 discusses energy storage procurement mandates. To what extent are states instead setting, quote, top line goals for the degree of hourly/seasonal alignment between clean electric supply and electric consumption, and letting energy storage be chosen among the tools to reach those alignment goals?
Very complicated question. I would say when it comes to seasonal storage slash long duration energy storage, we're not seeing much state policy activity yet with regard to that. The exceptions would be California, that's done studies specifically around the amount of long duration energy storage that it's going to need. There are other programs. New York has done some policy making on long duration, but again, it's hard enough to get states to start thinking about short duration energy storage. I refer back to those 35 states that have not done much, if anything. Getting them to start focusing on long duration energy storage is like the next evolution in this conversation. I would also point back to California as a unique state in its procurement mandate. It was the first of its kind that carved out a specific amount for behind the meter energy storage within a broader procurement mandate. So that was unique in itself, but it kind of set the path forward for this consensus that behind the meter energy storage assets have a critical role to play, and as aggregated resources can certainly start supporting the larger grid.
Great, thank you so much. I've got a couple of questions here from Brian Evans Mongion from Village of Hyde Park. We'll start with the first one here. He just asked simply, is there going to be a session in this program that will comment, address, or offer storage solutions for reliability needs?
Well, yes, I anticipate that that's going to be incorporated into that December 7th session that I referenced. By all means, for those here in attendance today, if there are key questions that you have that you'd like to hear from other New England states about what they're doing to address specific issues such as reliability and resilience, send them our way. We will make sure that they get incorporated into that session. So we have that flexibility to make this series the most valuable that it can be.
Absolutely. Thank you. And a follow-up question for him to that, or his second question reads, how does storage provide for decarbonization goals when the unit only temporarily holds generation from either a specific source or the grid? What am I missing here?
Well, we cannot achieve decarbonization without energy storage due to the fundamental intermittency of renewable resources. So if a state puts into place a decarbonization goal, the backstory to that is the inherent need for energy storage as well. We're going to need ever and ever longer durations of energy storage as we meet thresholds of renewable penetrations, somewhere around 60% to 70%. There are differences in the study findings of that. But as we get to that level of renewables penetration, we're going to absolutely need ever longer durations for energy storage. So you can't really separate the two. My concern is that the states that have adopted these decarbonization plans, the 19 that I mentioned and showed you in that chart, the majority of them have still not done that type of a study saying, okay, exactly how much energy storage are we going to need to support our decarbonization goal? Where should it be placed? How long durations are we going to need, et cetera? So there's a lot of modeling work that still needs to be done in that regard. And I think we're out of time, unfortunately. So I'm going to turn it back to John Cotter to say some follow-up remaining comments. John?
Thanks, Will. That brings us to 3 o'clock and the conclusion of our first session in this 5-part series. I want to thank our presenters today, Dr. Zook, Eric Sporky, and Will McNamara. I also want to give a shout out of thanks to Dylan Poindexter, who was the disembodied voice you heard a few times today. He was running our platform for us, so certainly his help was absolutely invaluable. So thank you very much, Dylan. I'd also like to thank everyone that has attended today. We hope it proved useful. It was really just our initial dive into this pool. Our next session will take place next Thursday. Again, it will be from 1 to 3 p.m. Eastern Time. Next week, we will cover part 1 of a 2-part presentation on the installation and operation of energy storage systems. More detailed information on next week's agenda, as well as the agenda for all of the remaining sessions, can be found in the Commission's order announcing this webinar series. And you can find that by using the Commission's online case management system, known as EPUC. And once you go to EPUC, you can look for case number 213883-rule. That's RULE, all uppercase letters. And when you arrive on that case page, you can select the tab Commission Issued Documents. And then from the list that follows, after you select that, you can select the document dated September 29th, 2023. It's titled Order Announcing Webinar Series, and it has a more detailed list of what can be expected in the upcoming sessions that we have. So thank everyone for their attendance today. Thank everybody for the work doing the presentation, and we'll hope to see all of you again next Thursday. Thanks very much.
Thanks, John. Bye-bye.
Bye, everyone.
Bye-bye.